Have you ever wondered how something the size of a finger can pierce armor as thick as a human body? Logically, it should just bounce off, but it doesn't, and it's not about size. It's what happens a millisecond before impact. The 2A82 tank gun on the T-14 Armada generates pressure inside the barrel of roughly 750 megapascals at the moment of firing. That pressure means nothing on its own, so consider this. Atmospheric pressure at sea level is 1 unit. The pressure inside a deep-sea submersible at the bottom of the Mariana Trench exceeds 1,000 atmospheres. Inside a tank gun barrel, at the moment of firing, 750 of those atmospheres for a few milliseconds. Then, 0. The round is already in flight, but there is one more figure that finally breaks intuition completely: the penetrator rod of an APFSDS round. The armor-piercing, fin-stabilized, discarding sabot has a diameter of roughly 22 millimeters and a length of up to 900 millimeters. That is an aspect ratio like spaghetti. That energy and that geometry are the answer, but most people look for it in the wrong place. They think more propellant means more velocity, heavier means more powerful, and that intuition fails from the very first second. Many people assume a round travels faster if it is heavier, with more propellant, greater pressure, greater impulse, and a higher final velocity. But here is the problem. Newton's second law: acceleration equals force divided by mass. The same propellant pressure acts on the round for the same duration inside the barrel. If the mass is halved, the acceleration doubles. Physics does not ask what you consider logical. Now add kinetic energy. The formula: 1/2 of mass multiplied by the square of velocity. The square. That means if you double the velocity, the energy quadruples, not doubles, quadruples. That is why engineers deliberately accepted a reduction in mass in exchange for a sharp jump in velocity. The mathematics proved more profitable than intuition, but velocity and mass are still not the full picture. There is a third parameter that decides everything: pressure at the point of contact. Imagine a stiletto heel and the wide sole of a winter boot. The same person's weight, but the pressure on the floor differs by tens of times. That is why the stiletto pierces a parquet floor, and the boot does not. The armor-piercing fin, stabilized, discarding sabot rod is the stiletto. The high-explosive fragmentation shell is the boot. All the kinetic energy is concentrated on a circle 22 millimeters in diameter, not distributed, concentrated. What actually determines everything is specific kinetic energy per unit of cross-sectional area. How much energy is focused on that tiny circle where the round meets the armor? Armor penetration is not mass, and not velocity in isolation. It is pressure at the point of contact, concentrated in the smallest possible diameter at the highest possible velocity. The first system is the round itself, more precisely, its shape and the way it is fired. A standard high-explosive shell fills the entire diameter of the barrel. It is heavy and wide, and moves slowly, around 900 meters per second, for most 125mm ammunition. The sub-caliber round, an armor-piercing fin-stabilized discarding sabot round, is an arrow-shaped tungsten or uranium rod with a diameter of roughly 22 to 30 millimeters, fired from a gun with a bore of 120 or 125 millimeters. It is 4 times narrower than the barrel. How do you fit a narrow rod into a wide barrel and still use all the propellant pressure? The answer is the sabot. The discarding sabot is typically 3 aluminum petals that fill the space between the rod and the barrel. All the force of the propellant pushes the sabot, and the sabot pushes the rod. At the muzzle, aerodynamic drag instantly strips the sabot away to the sides, and only the rod continues in flight. Imagine throwing a spear that is too thin for your hand to grip. You hold it inside a glove that perfectly fills your grip. You throw it, the glove flies off, and the spear keeps going. Exactly that. The sabot is the glove, needed only for the shot. The sabot is made of aluminum. Because it must be light, it does not travel to the target, it only transfers the impulse from the propellant to the rod. The American M829A3, the Russian 3BM60, the British L27A1, and the German DM63 are all built on the same principle. The rod flies to the target, and the sabot falls away between the tank and the target. Here is a detail almost no one knows. The sabot petals fly off to the sides at several hundred meters per second, and within about 30 meters of the tank, they are lethal to an unprotected person. Not the round, the wrapper around the round. That is why the US Army has specific protocols. Infantry does not stand to the side of a tank when an armor-piercing, fin-stabilized, discarding sabot round is fired. This is not theory. These are documented incidents on test ranges, and the stabilizer fins at the tail of the rod, small metal pedals, keep it on axis in flight rather than using rifling, because rifling at that velocity would simply destroy the thin rod. But there is another system that almost no one accounts for, and it breaks everything we just established. What is it made of, and why is that not simply a question of hardness? The first option is tungsten, the most refractory metal in practical use. Hardness on the Mohs scale of 7.5 out of 10, harder than most structural metals. A tungsten rod packs maximum mass into minimum diameter, and that directly increases specific kinetic energy at the point of impact. Most NATO countries use tungsten alloys in variants without depleted uranium. Examples include Japan, Israel, and Germany with the DM53. Tungsten. The second option is depleted uranium. The US uses it in the M829, Britain in the L27, and in certain Israeli designs. Depleted uranium is a byproduct of nuclear fuel enrichment, non-nuclear in the weapons sense. But density is not the main point here. The main point is what happens at the moment of impact. Depleted uranium. This is where an effect appears that changes the entire logic of penetration. Tungsten, under contact with armor, deforms in a mushroom shape. It expands at the tip like a crushed bottle cork. The end of the rod flattens, the effective contact diameter increases, and the pressure drops. This is the physics of plastic deformation. The metal does not have time to fracture and simply flows sideways. Deforms. Depleted uranium behaves in a fundamentally different way. It shears off in microlayers at the point of contact and remains sharp throughout the penetration process. Imagine a pencil that sharpens itself as you write. The tip does not flatten. It shears off in thin layers and stays sharp. That is exactly what uranium does under the extreme pressure of impact. Physicists call it adiabatic shear failure, but the essence is simple. The metal has no time to transfer heat to adjacent layers. It locally ignites and flies away. The rod sharpens itself in the process of penetrating, self-sharpening. That is precisely why the M829A4, the longest APF SDS currently in US Army service, roughly 900 millimeters long with a diameter of 26 millimeters, penetrates the equivalent of over 800 millimeters of rolled homogeneous armor under standard NATO testing, not because of the metal itself, because of how the metal behaves under extreme pressure. But depleted uranium has another side, one not discussed in technical brochures. After Kosovo and Iraq, elevated rates of cancer were documented among veterans and local residents in areas where depleted uranium munitions were used. Balkan syndrome. NATO officially denied any link until 2001, until parliamentary investigations in Italy and Belgium forced an acknowledgement of the problem. Depleted uranium partially vaporizes on impact and settles as radioactive dust. This does not make the weapon less effective, but it is a real cost of an engineering decision, paid by people who are not engineers. But there is one more level, and it is not in the metal, not in the shape of the rod, it is in what happens on the other side of the armor. But armor is not a passive obstacle. It evolved in response. Modern composite armor is not simple steel plates. It is a package of different materials, high-strength steel, ceramics made from aluminum oxide or boron carbide, polymer layers of ultra-high molecular weight polyethylene, and sometimes voids with calculated geometry. Modern frontal armor works sequentially, and each layer responds to the round in a different way. Ceramic is the first and most important layer. Boron carbide has a hardness second only only to diamond. When the penetrator rod strikes the ceramic, two processes occur at once. The ceramic disrupts the rod tip or forces it off axis, and at the same time, the ceramic shatters into powder, absorbing kinetic energy as it destroys itself. This is not a weakness of ceramic, it is its job. It is supposed to break, and to break in a way that takes as much energy as possible with it. The steel layer behind the ceramic receives a rod that is already deformed and slowed. If the ceramic did its job, the rod may fracture into several fragments, each of which no longer carries enough specific energy to keep penetrating. If it did not, the steel takes the residual impact. There is one more layer of protection, and it is not passive. Reactive armor uses tiles of explosive mounted on the tank outer surface. These tiles are known as explosive reactive armor, or ERA. They detonate toward the incoming round and try to shatter or destabilize the rod before it reaches the main armor. Russia's Contact 5, Israel's Trophy, and the American Tusk on the M1 Abrams all operate on this principle. Against shaped charged jets, explosive reactive armor is almost fully effective. Against armor-piercing, fin-stabilized, discarding sabot, spelled APFSDS, it is only partially effective. The explosion can deflect the rod off axis, but it cannot remove its kinetic energy. This is the arms race at the micro scale. Every solution generates a counter-solution. Every defense generates a new round. But there is one more element not discussed in basic explanations: the angle of engagement. If the armor is angled, the round travels through it diagonally, not through 300 millimeters of steel, but through 600 millimeters. The same plate, twice as thick simply because of the angle, and simultaneously, a lateral load is placed on the R-rod. The same rod that is the perfect weapon on a direct hit breaks under its own bending moment on an oblique strike. Imagine trying to push a needle through several layers of dense fabric at an angle. The first layer deflects the point, the second breaks the tip, the third simply absorbs whatever force remains. Each layer is calculated for the specific residual condition of the round after the layer before it. And here is the honest part. Engineers can calculate penetration against homogeneous armor using standard methods. There are formulas, there are range tests, there are documented results. But a real engagement is not a range. It is an angle of impact that can shift at the last moment because of uneven ground. It is armor damaged by a previous hit where the ceramic has already done its job once and will not recover. If you want to understand how armor answers that impact, the next video is already there.